Okay, hi, this is Theodore Norvell. Um, I just wanted to do a little extra video because we covered most of what you need for assignment one, but in the class we didn't cover all of it. It is covered in the extra reading, in the assigned reading, which is the proof outlines logic paper, which I've put on the website some time ago. Anyway, but I wanted to go through the material. I will be going over this again on Monday, but in case you wanted to work on the assignment on the weekend and wanted to, or maybe you've worked on the assignment, but you just want some confirmation that you were doing the right thing. So here we go. A very quick recap. We want to show that commands are in some sense correct. We call this partial correctness, and partial correctness means that if we start in, well, partial correctness is with respect to some specification, and the kind of specification we're going to use is a contract. Okay, so a contract is something like this. It's got a precondition and a postcondition, and conditions are just Boolean expressions that involve variables that might be variables of the program state. Usually they are, and by convention I'll use lowercase for those, or they might be specification variables, and usually I use uppercase for those. And sometimes it doesn't really matter if a variable is a state variable or a specification variable because, as long as we don't change it, it actually doesn't matter. If we do change it, it better be a state variable. Okay, so all right, so we have a specification that consists of a precondition, which I call P here, and a postcondition R. Okay, and then we have a command, and the command is partially correct with respect to the specification. If for any state that we start in where P holds, either execution never terminates, so the command goes into an infinite loop, or the execution does terminate, and we end up in state R. And in the course, in order to end up in state R, in order for the execution to terminate successfully, we need that no errors occur. And we're going to ignore errors for now. I might do a separate video on errors later on, but if I get time. But for now, we're just going to pretty much ignore errors. Okay, so that's partial correctness. Now, there's a whole chain here. So to show, that's what we really want to show, is that a command is partially correct. In order to do that, we're going to annotate the command with internal assertions, and we call that command, together with the pre and post condition, we call that a proof outline. So the first step in the chain is we're going to show that proof outlines are correct. And it turns out there's rules that we can follow to do that. And if we can prove the proof outline is correct using those rules, we will call it a provably correct proof outline. So there's a chain here. We're going to show that a proof outline is provably correct, which means that the proof outline is correct, which means that the command is correct with respect to the pre and post condition. That will be actually part of the proof outline. Okay, so we've gone through the syntax of proof outlines before, and we have this idea that a proof outline is correct. Okay, partial correctness for a proof outline means that if we start in an initial state where P is true, okay, and we execute the command, then first off, no errors occur during the execution. Secondly, each time we reach an internal assertion, then that internal assertion will hold. That is, it will be true of the state at the time that we reach the internal assertion. And finally, that should also be true for the post condition. So if we ever reach the post condition, that is, if the program ever terminates, then R will hold. And so we call that partial correctness of a proof outline. And what we want to do is to show that proof outlines are partially correct. And the way to do that, well, the way we're going to do it, is to reduce the proof outline, or the correctness of the proof outline, to showing that a number of verification conditions, so-called, are all universally true. That is, that they always hold. So universally true just means that a condition always holds, no matter what the variable values of the variables involved in the condition might be. Okay, it's very important that given verification condition, it's either universally correct or it's not universally correct. It's one or the other. Sorry, universally true or not universally true. It's one or the other. There's really no in between. Okay, we're going to start with some proof outline here, and we're going to reduce it to a set of verification conditions, and then we'll show that each of those verification conditions is either universally true or is not universally true. If we can show that they're all universally true, then that means that the proof outline is correct, and we're done. If one of those verification conditions is not universally true, well, it means that our effort has failed. So there's many reasons that that might happen. One is that the proof outline is actually not correct. Another is that it is correct, but we we can't show that it's correct using this technique. And in that case, what we usually want to do is go back and change the annotations of the proof outline. Often what we need to do is strengthen a loop invariant. We'll see that later on. But what we need is some rules to turn proof outlines into a set of verification conditions, to turn each proof outline into a set of verification conditions.